Welcome everyone. This is Separation Processes course presented by me, Saiffulla. Our topic today is the single stage distillation. First, what do we mean by single stage and what do we mean by distillation? As we said in the previous video, the stage is a place where the vapor and liquid meet each other. And if they have one space to meet, one room only to meet, so this is called a single stage. Okay, this is a single stage process. If I have only one place where the liquid can meet the vapor, or any two phases can meet. And what do we mean by distillation? Distillation is a technique to separate the components from each other. In distillation, if I have two components, for example A and B, and then I heat it up, okay, for sure the boiling point of B is different than the boiling point of A. So as I heat, the more volatile component will leave the system and then I can collect it, right? And the heavier component will stay at this system. So as you can see, I'm separating A from B based on the difference in the boiling point. And this technique is called distillation. And we have batch distillation and continuous distillation. Today, our focus will be on the continuous distillation, where we have a continuous inlet and continuous outlet. So it is not batch, it is continuous. And we are going to assume that the process is steady state, so there is no accumulation with time. Let's see how we are going to deal with such problems. First, let's draw this box to represent a single stage distillation. So this is only one stage, where one place that the vapor can meet the liquid. And let's say that I have a stream going into the system, and this stream composed of liquid and vapor. Okay, so maybe I have a heater here, and I have a liquid vase, and then I heat it up to produce liquid and vapor vases, and then I provide a room for them to meet each other. Or if I have a vapor here, so I produce a cooler, then I can get liquid and vase vapor, and then I provide a room or space for them to meet each other. What will happen when they meet? The liquid will go down because of the gravitational force, and the vapor will go up. Okay, because the vapor is lighter. Okay, it has a lower density, so it will go up. So I can provide two streams there, where the top stream will be vapor and the downstream will be a liquid. Okay, so this feed, let's call it F, and let's say that this feed has a specific composition, for example in mole fraction, and let's call it Zi, which is the mole fraction of the feed. And I could be A or B. This is if we have a binary mixture. Binary mixture means we have only two components, or even if we have multi-component system, C, D, etc. This all can be represented by I, Zi. It means ZA, ZB, CC, ZC, ZD, etc. Okay? First, we are going to talk about the binary system, where we have two components only, A and B. Then we will talk later about the multi-component system, where we have too many components, but still we are talking about the single stage. Okay, so let's assume I have a binary mixture at the feed contains A and B, and I produce a liquid and vapor, and then I provide a room for them to meet each other, and then I take the upward stream to be the vapor, which contains for sure A and B, and the downstream L, which contains A and B. But for sure, let's suppose that A is the more volatile component and B is the heavier component. The more volatile component has a lower boiling point, so it is easy to go to the vapor phase. So this product vapor will contain more of A and less of B, provided that A is the more volatile component. And this stream, the liquid, will contain more of the heavy component and less of the more volatile component, which is A. Okay, now how to solve such a problem? But before solving, let's agree on the symbols. So this F represents the feed, ZI represents the mole fraction of the feed, V represents the upstream, which is the vapor, and L represents this bottom stream, which contains the liquid, and the composition in the vapor phase, let's say it is Yi, and the composition in the liquid phase, let's say it is Xi. So let's agree on these symbols. Okay, suppose that you are required to calculate the composition in the vapor phase, or the composition in the liquid phase, or the vapor flow rate, the liquid flow rate. Usually the composition of the feed and the feed flow rate are given, or if there is no information about the feed, vapor or liquid, there is no information, you can take a basis for the feed, for example 100 kilomole per hour. Okay, but if there is given information, you need to stick with it. Okay, so how we can solve such a problem where we need to find either the flow rates or the composition either in the vapor stream or in the liquid stream? How we can solve such a problem? To solve this problem, we need to apply some rules. So let's draw the schematic again, where we have, this is the feed with a composition Zi, and this is the vapor with a composition Yi, and this is the liquid with composition Xi. By the way, this type of calculation called the flash calculation. When we say flash calculation, we mean single stage process. Flash calculation means the single stage process. Okay, and suppose for now we have a binary mixture where we have A and B, and A is the more volatile component. Okay, so how we can solve a problem where we need to find the flow rates or the composition? Simply, we are going to apply two things. We are going to apply the material balance, and we are going to apply the equilibrium relationships, the equilibrium relations. Since we say that we are going to apply the equilibrium relation, this means that there is an internal assumption that this stage reached the equilibrium. And what do we mean by the equilibrium state? The equilibrium state is where we have, this is the vapor and the liquid. The equilibrium is where the composition in the vapor and the composition in the liquid remains constant, and they are not changing in this stage. So each component A and B know his place. Okay, they are already distributed, and this distribution is not changing with time. So we have here in the vapor A and B, and in the liquid we have A and B. But if we say that the A is the more volatile component, so A will be more in the vapor, and B is the heavier component, so it will be more in the liquid. This is the equilibrium, and this is an assumption which usually works good. But for more analytical calculations, we need to provide the efficiency of the process, but يعني, there is no need to talk about the efficiency now. Let's assume we have an equilibrium situation. Okay, so first, as we say, we need the material balance and we need the equilibrium relations only. We don't need energy balance, we don't need momentum balance. That's why separation processes is an easy course. Okay, so first let's apply the material balance. It is a simple material balance. First, the overall material balance, F equal V plus L. This is the overall material balance. We can say F is equal to V plus L. And if we apply the component material balance, we just multiply by the composition, the mole fractions. Okay, so the component material balance will be ZIF is equal to YIV plus XIL. This is the component material balance. For simplicity, let's define a quantity called the vapor percentage in the feed, and we are going to call it mu. Mu is equal to the amount of vapor produced from the process divided by the feed, and we will call it the vapor percentage of the feed. Okay, and for the liquid we will have a same quantity called the liquid percentage, and it is, instead of vapor, it will be liquid over the feed, or in other way it is 1 minus mu, 1 minus the percentage of the vapor. So if we have, for example, 60% vapor, this means that we have 40% liquid in our system. Okay, so this is just a new definition that we introduced to simplify the equation. So we have this equation. We can divide both sides by F. If you divide both sides by F, you will get that ZI is equal to V over F multiplied by YI plus L over F multiplied by XI. This quantity V over F is nu, and this quantity L over F is psi, which is 1 minus mu. So this will be 1 minus nu. Okay, so we can rearrange to get that ZI equal to YI multiplied by nu plus, which is the vapor fraction, and 1 minus nu multiplied by XI. Okay, so if we want to rearrange this equation to get the composition of the vapor phase in one side and the other on the other side, we're going to move this here and divide by this both sides, so we will end up with this relation, which is YI is equal to nu minus 1 over nu XI plus plus ZI over nu. So this equation is called the material balance equation. This equation is called the material balance equation, or we can call it the Q-line equation. The Q-line equation. So this is our first equation. Now the second equation will be, so this is our first equation. The second equation will be the equilibrium relationship equation. And how we are going to find this relation? Okay, first let's define something called the distribution coefficient K, which we have discussed in thermodynamics, chemical engineering thermodynamics. This distribution coefficient is defined as Ki is equal to the composition in the vapor phase Yi over the composition in the liquid phase, the Xi. And let's define another quantity called the relative volatility. Relative volatility. Okay? Let's say that we have a two component 1 and component 2. So the relative volatility 1 to 2 for the first component to the second component is simply the ratio of the distribution coefficient for each one, K1 over K2, which is 1 and 2 or A and B, anything, could be anything, which is Y1 over X1 and Y2 over X2, okay, from this equation. And we know that X2 is equal to 1 minus X1 and Y2 is equal to 1 minus Y1, 1 minus Y1, because the summation of all X's molar fraction in the liquid phase is equal to 1 and the summation of all molar fraction in the vapor phase is equal to 1. So we can substitute these two here, okay, and then we can rearrange to get this relation. Y1 is equal to alpha 1 2 multiplied by X1 1 plus X1 multiplied by alpha 1 2 minus 1. This is upon rearrangement. Okay, one thing that I want to mention, when we say Y1, we mean the mole fraction in the vapor phase for the more volatile component, so we can say it is only Y. So when you see Y with nothing, this means the mole fraction of the more volatile component. Similarly, when we say X1, we can say only X with no subscript, and this refers to the mole fraction of the more volatile component in the liquid. And this refers to the mole fraction of the more volatile component in the liquid phase. Okay? So now this is the second equation, which is the equilibrium relation equation. So we have two relations, Y with nothing. This means for the more volatile component is equal to alpha multiply alpha 1 2, or simply alpha because we have binary system. So we have one relative volatility. So it will be alpha X 1 plus X alpha minus 1. So this is the equation that we get from the equilibrium relation. The other equation from the material balance, which is the Q line equation, as Q is equal to the vapor percentage minus 1 over the vapor percentage multiplied by X plus Z over the vapor percentage. Usually, in most of the cases, the vapor percentage will be given, or the liquid percentage will be given, and then you can find the vapor percentage from 1 minus the liquid percentage. Okay, and usually the composition of the feed is given. Okay, and usually the relative volatility is given, and after a while we will talk about the cases where the relative volatility is not given. But now let's suppose that the relative volatility is a given. So you can say that we have two equation 1 and equation 2, and we have two variables, y and x. Two equations, two variables, so I can solve them simultaneously. Okay, it is like mathematics when you have two equations and two variables, so you can solve them simultaneously. For the case where the relative volatility is given, you can solve them analytically or in other words, algebraically. Where you use algebra, you can say that this is y and this is y, so this side is equal to this side, and you can use a solver to get x, and then after you get x, you can substitute in one equation and get y. This is for the case where the relative volatility is given. And the other case where the relative volatility is not given, keep in mind that the first equation is obtained from the equilibrium relation, the second equation is obtained from material balance. The equation obtained from material balance does not contain the relative volatility. Okay? So it doesn't matter, it will not change. But the first equation, which contains the relative volatility, and we assume it is given and it is constant. Okay, so if we don't have a constant relative volatility, we are not given a relative volatility, so we need another way to solve the problem. The other way is to use the graphical solution. And what do we mean by the graphical solution? The graphical solution is that this line, the material balance line, will be fixed, but we will not have this equation because this equation depends on the relative volatility. Instead of, we will have an equilibrium data x and y with specific values obtained experimentally. And then what I have to do, I need to solve graphically. How I am going to solve graphically? From mathematics, you know that if I have two functions and they intersect on a point, this point of intersection will be my solution. We are going to apply the same thing. If we are given the equilibrium data, we are going to plot them. We will draw our axis, the x, which is the mole fraction in the liquid phase, y, the mole fraction on the vapor phase. We are going to plot the points given, and then we are going to connect them. Okay, so this is called the equilibrium relation. Now, what about the mass balance, material balance relation? You can see that this equation, let's write it again. Y is equal to nu minus 1 over nu x plus z over nu. And remember that when we say y was nothing, x was nothing, z was nothing, we mean x, y, and z for the more volatile component. Okay, only for the more volatile component, which has the lowest boiling point. Okay, so you can see that this equation is like slope-intercept form. So this is my intercept, and this is the slope. Usually, as we say, the vapor fraction will be given, so you can find the slope, and the intercept, usually z will be given, the composition in the feet, so you can find the intercept. So you can go and determine the y-intercept. Maybe let's say it is here. Okay, you determine the y-intercept, and then you use the slope. You apply mathematics. You use the slope to determine any other point. Maybe it will be here, using the slope, and then you can connect between the points, and the intersection will be my solution. So this is the graphical solution. The intersection will be my solution. This will be the composition of the more volatile component in the liquid, and this will be the composition of the more volatile component in the vapor vase. So when I have the equilibrium data, I don't have constant relative volatility. I need to use a graphical solution, and the solution simply will be the intersection between what? The material balance curve and the equilibrium relation curve. Okay? So this, and keep in mind that This way of solution, either using a graphical solution or you use algebraic solution with two equations, this is only valid if you have binary mixture. This is only valid if you have binary mixture. Now, if you have multi-component system, so now the second case, we are going to talk about case 2, where I have a multi-component system. When you have multi-component system, keep in mind that you cannot use graphical solution. Why? Because graphical solution is only 2 axes. Okay? You cannot do more than 2 axes. It will be difficult or time consuming. So we are in the multi-component system, we are going to rely on the analytical solution using not perfect analytical, because we are going to use some approximation in finding the roots, as we will see now. Okay, back to that definition. The definition of separation processes problems: we need material balance and we need equilibrium relationships. For the multi-component distillation, we are going to assume that we are going to assume that we have a constant distribution coefficient, Ki. Okay, and first we are going to derive a formula, this formula called the Rashford-Rice equation. This formula is called Rashford-Rice equation. This equation will be used for the calculation of the multi-component distillation, but keep in mind we are still talking about the single stage. We have only single stage. But now I have multi-component system, like I have A, B, C, etc. Could be 3 or more, this multi-component distillation. So I cannot rely on the graphical solution. I cannot have 2 equations and solve the 2 equations simultaneously. I need to rely on another way. But the base is the same. We are going to use the material balance and we are going to use the equilibrium relationships. So the basic will remain the same. And how we are going to apply it? Let's draw our schematic. This is the vapor, this is the liquid, this is the composition in the liquid, and this is the composition in the vapor. This is the feed, and this is the composition on the feed. Okay, now let's write the overall material balance. F is equal to V plus L. The component material balance, ZIF, is equal to YIV plus XIL. Okay, let's divide by F both sides. Okay, so here F will be cancelled, and now let's deal with the liquid fraction, which is the liquid over the feed. Okay, so this guy L over F will be this, and this guy V over F will be 1 minus the liquid fraction. Okay, rearranging the equation, we will get that Zi is equal to the liquid fraction multiplied by the molar fraction in the liquid phase plus 1 minus the liquid fraction multiplied by the molar fraction in the vapor phase. Okay, now let's introduce the other relation, which is the equilibrium relationship. And let's assume that we have a constant distribution coefficient. So the distribution coefficient is ki is equal to yi over xi, or in other words, yi is equal to ki xi. So let's put this here. Okay, and then let's rearrange the equation and put xi on one side. We will get that xi is equal to zi 1 plus psi, the liquid fraction, multiplied by the distribution coefficient minus 1. Okay, and we know that yi is equal to kixi. So similarly, we can write that yi is equal to xi ki, which is equal to the same formula here multiplied by ki. So we have two equations, one equation for xi and the second equation for the yi, and both are derived based on the material balance and the equilibrium relationship. Keep in mind that the heart of this course is the material balance and the equilibrium relationships. This is the heart of this course, the main equations, and we are going to play with them only. Okay, from definition we know that summation of mole fraction in the liquid phase is equal to 1, summation of the mole fraction on the vapor phase is equal to 1. In other words, summation of the xi is equal to the summation of the yi, right? Or in other words, summation of xi minus summation of the yi will be equal to 0. Okay, so what's xi? Here is xi. So the summation of xi will be the summation of this. And what is yi? What is yi? This is yi, the same quantity multiplied by ki. So the summation of yi will be the summation of ki multiplied by this quantity. Okay, so we will get that the summation of zi 1 plus psi multiplied by ki minus 1 minus summation of ki zi 1 plus psi multiplied by ki minus 1, so it is the same quantity but with ki is equal to 0. So we have here the summation. We can take a common factor, which will be the summation of zi 1 minus ki. I take a common vector zi, so the remaining is 1 minus ki over, and the denominator is the same, so it will remain the same, the denominator, 1 plus psi ki minus 1 is equal to 0. This is called the Latch-Race equation, and it is a very, very important equation that combines the material balance with the equilibrium relation to solve the problems that contains the multi-component distillation or multi-component flash calculation. Why it is a flash calculation? Because it is single stage. Okay, so if I have, for example, 3 component, I am going to write this term 3 times, z1, k1, psi will be the same, and k1. I am going to write it 3 times. Okay, usually Zi, the composition of the feed, will be given. The distribution coefficient will be given. This distribution coefficient will be given for each component. And you are going to find this, the psi. So you will get nonlinear equation. Nonlinear equation because psi is in the denominator and it is added to 1, so it is a nonlinear equation. So you need to use solver, or you can use numerical methods like Newton-Raphson methods and secant method, etc. But the easiest way is to use the calculator solver. But in your calculator solver, you need to write an initial guess, and a good initial guess, this is the liquid fraction. Remember that this psi is liquid over feed, so it will be, this psi will be between 0 and 1. So you can take initial guess 0.5, for example, as an initial guess, because if you take initial guess 10 or -2, etc., you may get another solution, because nonlinear equation have many solutions. Okay, so you need to choose a right initial guess between 0 and 1 to find this psi. After you find psi, you will say that psi is equal to L over F. Usually the feed is given. If it is not given, you can take a basis 100 kilomole per hour, for example, or anything. So you can find the liquid flow rate. After you find the liquid flow rate, you can say that the liquid flow rate is equal to the feed minus the vapor from the material balance. Remember this, feed equal V plus L. Okay, so you can find the liquid. Suppose if you are required to find Xi and Yi, they are easy to find. You are going to find it from here. So X, for example, X1 will be Z1, 1 plus psi, which you determined from the solver, K1 minus 1. And X2 will be the same, but Z2 and K2. And X3 will be same. And then the Y, how to get, so let's rewrite it again. So Xi you can get from Zi 1 plus psi Ki minus 1, and remember that Ki is equal to Yi over Xi. So Yi you can get it directly, the composition in the vapor phase. You can get it by rearranging this equation. It will be Xi Ki. So you can find the composition in the vapor phase if it is required. One last thing that I want to mention before finishing this video: what if the distribution coefficient Ki, which is Yi over Xi, is not given in the problem? What you have to do? Okay, so remember the Raoult's law. The Raoult's law say that YIP is equal to XIPI sat. This is the Raoult's law, if you remember from thermodynamics. Or the modified Raoult's law. If you have modified Raoult's law, you need to add the gamma variable or the gamma parameter, which accounts for the non-ideality of the solution. But suppose we have ideal solution, so gamma is equal to 1. But same procedure, if you have non-ideal solution, you need to add gamma I. So what will happen if I take this P here and I take this Xi here? You will get that Yi over Xi is equal to Pi sat over P. And what is this? What is Yi by Xi? Yes, you got it right. This is Ki, the distribution coefficient. Okay, so you may not given the Ki, but if you are given the saturated pressure and the total pressure, you can divide them and get the Ki. Okay, or if you have the pressure and you have, for example, the temperature and A, B, C, the coefficient of the Antoine equation, you can use it to get the BI set. Okay, so you don't have to have this distribution coefficient, you can find it indirectly using the Raoult's law or the modified Raoult's law with activity coefficient. That's all for now. Thank you for your listening. I wish you all the best.